All right, this is the start of the recording, but we still have a little over 2 minutes. Eight, seven, six, five, four. Yeah. All right. Okay. It is Tuesday, April 21st. At 8:50 a.m. So we'll do these warm-ups in a second. Um, just a round of announcements first. Oh, come on. Oh, yeah, I have to select the screen. There we go. Um, so quiz today. Today's a Tuesday, so please do the online quiz. Remind you that again at the end of class for anybody who needed to join late or watches the end of the clip instead. Um, Please keep current with web work. What that means for April 21st for today means after today's class, please think about starting web work number 36. Sometimes what happens, I'm not saying you have to finish this assignment. I mean, if you do, great. But like I think what sometimes happens is people kind of fall into this trap of just always starting the assignment that is due that day. And that's stuff from a while back. It makes tuning into class, the stuff that goes on doesn't make as much sense. It also leads to, I think, a lot of frustration and anxiety, just in terms of um, like not getting a chance to get everything done or get your questions answered, things like that. So please think about starting sooner. Um, uh, Again, meaning don't just because WebWork 33 is due today, it's not a good reason to start that assignment today. It happens on occasion, but I'm trying to be a little more creative with what I'm doing with the announcements and including now this daily info of what assignment I would suggest you strongly start. So I'd like to go through these warm-ups. The first one here, antiderivative of, well, one thing times another. And one of the key warnings I wanted to talk about yesterday is it's so tempting for people to just try to anti-differentiate the first part and then anti-differentiate the second part and then multiply the results together. That's a made-up product rule for integrals. That doesn't work. It leads to a totally different answer than the actual one. So we have to do something else. And well, if we don't want this product here, why don't we expand this out by foiling, right? By multiplying. And that step, so sorry for, I know this problem number 2 is getting in the way, but this took up all the room. So I just have this equals, meaning equal to what the original question was. But I've got here equals integral sign. And this integral sign or antiderivative notation is here because we are not yet ready to compute the antiderivative. So this is an algebra step. to do this expanding, this foiling, right? 4x to the 6th times 10x to the 3rd is 40x to the 9th. The 9 is because when you multiply things with the same base, you need to add the exponent. So x to the 6th times x to the 3rd is x to the 9th. Same deal, right? 4x to the 6th times 2x to the negative 7th is 8x to the negative 1st. 3x to the negative 2nd times 10x to the 3rd is 30x to the 1st. And 3x to the negative 2nd times 2x to the negative 7th is 6x to the negative 9th. That step, again, is an algebra step. So we have not computed an antiderivative yet. So where the original question says antiderivative of, we still have this symbol here that means antiderivative of. I'm actually in the next 2 steps going to show quite a lot of extra work, and if you whether right now in your own notes or for like a quiz or exam choose not to show this much work, I get it, that's fine. I'm going to show these next 2 steps though to illustrate a certain point, that's all. So now the point is when you have an antiderivative question and there's these 4 terms, with, separated by the 3 plus signs, you can split this up. So I've now taken this one integral dx of a function with 4 terms and split it up into 4 separate problems. So integral sign dx, antiderivative of 40x to the 9th. And then the next little antiderivative problem is antiderivative of 8x to the negative 1st. So this second term from up here, still with a dx at the end. So you'll see it's a lot of writing, yeah, but integral sign dx, that happens 4 times, once for each of the terms. Again, you probably get to a stage where you're like, I don't want to write all that down, and I'm not expecting anybody to write that down. But since this process is new, it doesn't hurt for me to just show every little detailed step for one. And then part of the reason to show my steps right now is to make a point by the end of the problem as well. Okay, again, this next step from here, so not just, you might skip writing this step, but even if you wrote this step, you might skip writing the next step. But I'm going to include it to, again, just take it one thing at a time for one and to illustrate a point by the end. You can take this 40, you can bring it in front. Right, a fixed number. So just like with derivatives, you have a fixed number in front of a function, you can bring that in front. Same deal here. So bring the 40 in front, bring the 8 in front, bring the 30 in front. You get a thing that looks like this. Again, you probably want to choose not to write this in the future. I get that. What I want to do now is say, okay, let's take a look at like this antiderivative problem right there. Now we're ready. Let's compute that, right? So this is not, don't differentiate x to the 9th. We need to undifferentiate. We need to anti-differentiate. So what's going to differentiate to produce x to the 9th? And we had this rule for antiderivatives that was based off of the power rule, where now we have to raise the exponent by 1 and divide by that number. So the 40 was copied, but we have x to the 10th over 10 as the antiderivative of x to the 9th. And then I copied the 8. Sorry, the 8 was over here. Now it's spacing-wise, it just doesn't take up as much room. That's all. And then the antiderivative of x to the negative 1st dx is ln of absolute value of x. Copied the 30, which is over here. The antiderivative of x to the 1 is x to the 2 over 2. And I copied the 6. And then to anti-differentiate x to the negative 9th, you have to raise the exponent by 1. So negative 9 plus 1 is a negative 8. So x to the negative 8, still then divide by that new exponent. So divide by negative 8. And having computed all our antiderivatives, there's a plus c at the end of this. The key thing I want to say about this step, though, is, so this step is definitely worth writing down. The key thing about this step is it has no more integral signs in it. And that's because we computed the integrals. We found antiderivatives. We found 4 antiderivatives, right? This x to the 9th is not equal to x to the 10th over 10. It's the antiderivative of x to the 9th is x to the 10th over 10. So having computed an antiderivative, we should no longer write the antiderivative symbol, because we computed it. And you could leave your final answer like this. That would be fine for me for this question. But to illustrate a point, I'm going to simplify. Again, this step is fine as a final answer for me. But I picked the numbers carefully in the beginning of the question because there'll be a lot of nice cancellations. 40 over 10. Can cancel a factor of 10 on top and bottom, be left with a 4. So 4x to the 10th. The second term doesn't simplify at all. The 30 over 2 does, as a 15. And then how about a 6 in the numerator and a negative 8 in the denominator? First of all, I just push the minus sign in front. And then 6 over 8 becomes a 3 over 4. And then just for funsies, because it could be done, instead of writing x to the negative 8th in the numerator, I wrote x to the positive 8th in the denominator. So 1 over x to the positive 8th. And still need to write the plus c. Okay, again, either of these two are okay as final answers to this question. The reason I'm doing the work that I did, though, so why simplify the algebra like this, is to talk about the following issue. Sometimes people get in this really strange thought process of saying, I need to, in these problems that have this new symbol, I need to write that symbol in every step except the final step. That's sometimes the habit people get themselves into. But you'll notice, to try to illustrate that point, this final step didn't have the symbol, yeah, but neither did the step before. So you don't want to get in this habit of saying, I just will draw the symbol in every step except the final step. That's not the correct approach, right? Like the thing to think about is, what does a symbol mean? This means the symbol means antiderivative of. So it's at the moment that you're computing antiderivatives, going from this step to this step, that you would no longer write the antiderivative symbol. So this requires a thinking of what the symbol means. So don't memorize this as, I write the symbol in every step except the last step, because that wasn't true here. Okay, again, even that I hope goes back to a little more clarity of why, to illustrate the point I was making. From here, from the original question to here to there to even to right there, none of that was doing any antiderivatives. So we kept writing the symbol. We kept postponing the work of computing or finding antiderivatives to do some algebra and some little manipulations like that. The other thing I should remind you all, is that you can always check your work by differentiating. It helps reinforce what the heck we're doing here. So we're not going to do this right now, but you should give it a try. If you take our final answer, you take this thingy right there, and then you differentiate it, you'll get something which, once you factor it, and it'll be kind of a little strange to factor, you'll get this stuff that was between the integral sign and the dx. You'll get that after you factor it. It'll be maybe kind of strange to factor, so you might want to just expand that instead. Okay, that's warm up 1. Warm up 2, if h is this, find h prime. This is a derivative question. So this is not antiderivative, this is derivative. And I obviously don't have room on this slide. I put it at the top of the next slide. Let's compute this derivative. This is going to require the chain rule, because this is a composition. We'll need the chain rule. And you may be in the habit of not showing all your work for the chain rule, and that's totally fine by me. You may still be in the habit of showing work. That's fine as well. But right now, I want to show the work because of how it's going to connect with what we do in a moment. So in this case, for our composition, the exterior function, capital E, by the way, it's E of U. We've been in the habit a lot of writing E of X, and that's fine too. But because of what we're going to do today, I'm going to use E of U. In fact, when we first learned chain rule, we actually had a U there, and it'll be very helpful in what we're doing today to have that U. So the exterior function is e to the u, and the interior function, I of x, is x to the fifth plus 6 to the x. So let's compute some derivatives. So capital E prime of u is e of u. So the thing is that e to the u is one of these kind of odd functions in that it is its own derivative. E to the u is its own derivative. And it'll actually come up. So actually, let's take a moment and say this. So e to the u is strange in that this function, coincidentally, it's its own derivative, but then it's its own antiderivative as well because of that. So think about it. So if this top e to the u, the derivative of this top e to the u is this bottom e to the u, then the antiderivative of this bottom e to the u ought to be this top e to the u. Okay, and that'll come up in just a moment, actually, so that's why I'm saying this. Over here, sorry for that interruption, we had I of x was this. We need to compute a derivative. The first term, x to the fifth, you differentiate using the power rule, you get 5x to the fourth. The next term, 6 to the x, you can't use a power rule there. You got to use that exponential derivative rule and get 6 to the x ln of 6. So here are all the pieces that we need for the chain rule. Since the function that we're given up here, just as a reminder, is in fact a composition, it is e of I of x, we can compute the derivative using the chain rule formula, which was e prime of I of x times I prime of x. First of all, the e prime of I of x, so we feed in to this e of u, this bottom e of u, we feed in I of x up here, and you end up with e to the power x to the fifth plus 6 to the x. I copy the multiplication symbol right there, and then we need I prime of x. So I prime of x I just copied right there. Because I prime of x has two terms, we are going to need parentheses. right? Because of order of operations issues. So that this has to be in parentheses. The multiplication symbol doesn't have to be written if you don't want, but the parentheses are required due to order of operations. So this warm up, we're done. We computed a derivative, but I want to illustrate a certain point. So I'm going to say the following. If we differentiate not just what we were asked to, but you also include plus a constant, that's not going to change the result of the derivative, right? So the result of the derivative we had before, I copied it down here in blue. Answer should be the same if you differentiate what you had before plus a constant, because a constant differentiates to 0. But you see these colors, and you saw this happen yesterday. You saw this also happen last Thursday. The reason for these colors is this switch that we're going to do here, right? So if this thingy ends up in this spot, that ends up in this spot. In order to do that, instead of having derivative notation, you need integral notation. So maybe with the drawn-in arrows on the slide, that's a little better, right? So derivative of what's in red equals what's in blue. Swap, so you need antiderivative notation. Antiderivative of blue, dx, equals what's in red. Okay, so the thing we're going to do in the next slide is talk about what if, so we're going to look at this statement here a little more carefully, but from the perspective of what if we were given this part right here on the left? What if you were given that, and then you were expected to produce what's here in red? Now, we're going to borrow some of the ideas from this slide on the next slide, in that we know that our final answer in red is going to be this, but how would we get that? So this seems like a strange process that you might be in just a week or so given a problem that looks like this and expected to produce that. How is that possible? It sounds very strange, but it can be done. And we're going to borrow just a couple ideas from this slide in the next slide, and also start to explore and build up a method. So it's going to be a little strange, but let me copy just what's there first. Like, that's the question. So suppose we were given integral of, or antiderivative of, e to the power x to the fifth plus 6 to the x, and then in parentheses 5x to the fourth plus 6 to the x ln of 6 dx. You're just given this question out of the blue. Like, you don't have the work that we have from the warm-up we just did, the second warm-up question. We will borrow from that in just a moment. But let's just say we were given this. Like, how does one go about attacking this question? This is the thought process that goes through my mind. First of all, let's just be clear what the question is, right? This integral problem, or this antiderivative problem, is saying find what you had to differentiate. Not differentiate the thing, but the derivative of something, fill in the blank, is e to the x to the fifth plus 6 to the x times quantity, what's in parentheses. So find what needed to be differentiated to produce what's between this symbol and the dx. This seems like a tall order, right? So here's the thing. If the function that you're looking for in this spot that would fill in this blank, if that function that you're looking for had to have been differentiated using the chain rule, if the function you're looking for was differentiated using the chain rule, what we really need to figure out is what the interior function was. We have to figure out what this interior function I of x was, though we'll call it u just because it's less writing. How do you find what this u, this interior function, needs to be? You're not going to like this answer. We have to guess. This seems so wrong in math somehow that we would be guessing, but we need to guess. I will, in just about 10 minutes, provide more information about how to guess well in this process, but for now, it seems like it should just be a wild guess, and we'll just kind of go with that. So how are we going to guess what u is? Well, right now, for the moment, we're going to go with u equals x to the fifth plus 6 to the x. This, by the way, in the second warm-up question, was what was the interior function. So we are borrowing this information from the warm-up right now. And you might say, how can we borrow that? Like, first question, let's kind of get through this and just borrow this information. And then in the next question, we'll talk about how do you guess without having to borrow from a warm-up. Okay, so in the warm-up we just did, literally the previous slide, this was the interior function, x to the fifth plus 6 to the x. What you do now is you compute the derivative of this thing. So let's not call it u prime, although that's valid. In what we're doing right now, the other derivative notation is going to be way more helpful. So d over dx instead of u prime equals 5x to the fourth plus 6 to the x ln of 6. So we computed a derivative. Then, so yeah, you might not have written down all this stuff right now. I get it, but like I hope you'll write down u equals x to the fifth plus 6 to the x, and that you wrote down du over dx equals 5x to the fourth plus 6 to the x ln 6. So get those written down. I know it's hard. I know this format's harder. It's harder to stay as active. I get it. So at least in these moments, we're like, oh, please write that down. Like, then it's a little easier to stay a little more connected to things by doing those sorts of things. Okay, the next thing we're going to do is we're going to solve for dx, but in two stages. So first, multiply both sides by dx. This sounds real strange, but multiplying by dx is going to look like this. So by multiplying by dx on the left side, the dx you introduce in the numerator cancels with the dx in the denominator. That's why you're just left with the du. On the other side, you had the two terms before, so let's wrap it in parentheses due to order of operations, and you have times the dx that we just introduced. This sounds so strange. This sounds so strange. I want you to think of dx like it's not two separate letters. Think of it like these two letters are glued together, and it's like a variable. Like instead of a dx, pretend it's a y or a z or an m or whatever, and it's two letters though. I get it, but like treat it like it's a single letter, and just multiply by that dx thingy on both sides. And because we're treating it as if it's just a single variable, even if it's written using two letters, let's now solve for dx. Now notice the right side is a thing in parentheses times dx. So to undo times, we've got to divide on both sides. So we're dividing both sides by 5x to the fourth plus 6 to the x ln of 6. So that's why now in this new equation, the left side used to be du, that's still in the numerator, over what we divided by, 5x to the fourth plus 6 to the x ln 6. On the right side, since we divided by what was in parentheses, we get that canceling out. All we're left with is the dx. Whew. All right, so we've solved for dx. Okay, this process I know seems a little strange, but what we're going to do is now we'll take the original question up here, and I know it's going to take a bit to rewrite it, but I would suggest doing that. It'll help in your notes kind of create like oh yeah, here's what we did, and then here's what we did. So integral e to the x to the fifth plus 6 to the x times quantity 5x to the fourth plus 6 to the x ln of 6 dx. Okay, here's what we're going to do. Let's rewrite all of this in this space right there after the equal sign with one exception. The one exception is we're going to replace this dx right there. Instead of writing a dx, you can replace dx with what it's equal to, so with this fraction. If you make that replacement, it looks like this. So for people who need to kind of review the slides kind of on their own time due to work or something right now, I put this piece in red so that people can kind of notice where this came from. So the integral sign is there. The e to the x to the fifth plus 6 to the x is there. This stuff in parentheses is there. It's just this dx right here, maybe I'll box it, got replaced with what's in this box right there. That's the only difference. So I know it's a lot of writing, but this is actually going to work out very well in just a moment. As you stare at this, I want you to notice in this new version of the problem after the equal sign, I'd like you to notice that this thingy right there is in the numerator and a copy of that is in the denominator. Those cancel out. Now I'm going to draw these slashes, but then I'm going to undo the drawing in a moment anyway. But those are gone, right? So they cancel each other out so that all you have is this integral sign e to that power and then just the du. So just the stuff where there's pen marking on it, that's all that's left in the next rendition of this. The one other thing though is here's where I shouldn't probably not have done the two steps at once, but this x to the fifth plus 6 to the x, we can replace that with a u. So that's the other replacement being made here. So just, I hope it's, okay, so this canceled with that, and then this piece, let me box it right here. Okay, this piece right there got replaced with this u right here, and that's from what's highlighted in red up there. Right, so integral sign, e to the what was in the box, but what's in the box can be replaced with a u. And then we have stuff that's crossed out because it canceled with stuff that was crossed out that was canceled, and all that's left is a du in the numerator, so that's why there's a du right over there. Maybe I'll get rid of all these markings. Sometimes the markings actually get in the way of allowing you to see what's happening. But check out what happened. The previous version of the problem had a mix of variables. There were x's, there were u's. Now this new version of the problem is way smaller. It only has u's, first of all. There's not x's and u's. It's only one variable, just u's, no x's and u's. And it's way smaller than the original question, which is just directly the line above. Way smaller. And here's the thing. Now that there's only one variable, let's answer the question. Let's compute an antiderivative. Here's where the comment earlier was helpful. The antiderivative of e to the u is e to the u. So here we're computing an antiderivative. That's why there's no more antiderivative symbol. There's no integral symbol. E to the u is its own derivative, so e to the u is its own antiderivative. We do need a plus c, though, when you antidifferentiate. And we're almost done. Notice the original question, which is still up here, didn't have any u's in it. We introduced the u's kind of temporarily. So now, at this point, let's take this, our answer so far, and we don't want any u's in the answer, so let's now replace the u with x to the fifth plus 6 to the x. So make that one tiny replacement here. E to the power, replace the u, still copy the plus c, and this will be our final answer there. This is a good place for me to pause because we're done with this question. We actually are recovering the information that was in red and blue at the end of the previous slide. But there's usually lots of questions. I had quite a number in the last section anyway, so let's just wait and see what comes up questions-wise. There's a lot related to the process that probably needs clearing up. But are there any confusions? Are there any wait, how did you go from here to here? Or how did you get from there to there? Or how did you get from here to there? Or anything like that? Anything at all? I'll just wait for a moment. Because there's always a delay between when I say it and then when you hear it and then when you bring up your question and then when I end up seeing it. So I'll just wait. Okay, I'm not seeing a question or hearing a question. Please bring up a question at any time in the process. What I would like to do then is to talk about this guess. How do you guess? How would you even begin to guess? And how would you know that you're making a good guess? Part of the feature that to notice is that this thingy here canceled with that there. That's a key part of the process. A cancellation needs to occur. So how are you going to make that cancellation occur? And how would you even know what to guess at all? Well, in this problem, I would like to note that this u equals x to the fifth plus 6 to the x isn't completely out of left field, right? Like if you look at the original question over here, at least somewhere in the problem, there is an x to the fifth plus 6 to the x, right? So just the fact that appeared somewhere in the problem means that somewhere in the question, u is probably hiding with the thing you need to guess for u. So I'm going to say it the following way. How do you pick u? It's usually in part of what you see. So here's a new question. We're going to do this question in full in a moment. But in this problem, integral of or antiderivative of the fraction 3x over square root of 1 minus x squared dx. What I mean by it's in part of what you see, I want to take this idea of like zoom in. So let's say this problem is written down, on a board, like really big, and then you walk super close to it and you zoom in. So I hope I don't make you dizzy in doing this, but like I'm gonna like really zoom in a lot. So I want to zoom in more, but as I do the pinching action, the screen won't let me here. But so I wish I could zoom in even more so that you don't even see the square right now. But if you zoom in enough, all you'll see is x. So maybe that's my u. Maybe that should be u. And then if I zoom out a little bit, just a little bit, then I finally see the square. And so maybe my u needs to be x squared. Okay, so that's maybe an option. But then if I zoom out a little more, maybe slide over just a little bit, I end up seeing this expression, 1 minus x squared. And maybe that's what u needs to be. But if I zoom out a little more, if I zoom out just enough, then I'll also see the square root sign. So then maybe my u needs to be this expression, root 1 minus x squared. Maybe, right? And then if I zoom out a little more, not zoom out a little more. Let's just say I go to the numerator and let's just zoom back in a little bit. I wish I could zoom in more, but the computer won't let me. Let's say if I zoom in enough, all I'll see is the x. So maybe that's what you use. Oh, we actually already said that earlier. If I zoom out a little bit, then 3x. Maybe that's what u should be, right? So those are at least some options of, so this idea of how do you pick u, kind of usually in part of what you see. So let me, I spoke a lot. I just so that you have it a record of this in the slides. I wouldn't write all this down right now, but some ideas, options for you. Here are some of the options I had mentioned. Maybe it's not all of them. Maybe there's a couple extras, but I just want you to get the idea. Maybe it's u equals x. Maybe it's u equals 3x. Oh, so I think when I designed the slides, I started with the numerator. Maybe it's u equals x squared. We had kind of mentioned that as a possibility. Maybe zooming out a little from the x squared, u equals 1 minus x squared. That expression. Zooming out just slightly more, u equals root 1 minus x squared. And then if you zoom out just a little more, this one's a little creative. But u equals 1 over root 1 minus x squared. So where would this come from? You have to kind of take that 3x and using algebra just push this off to the side. Right? So instead of being in the numerator of the fraction, you can always write it, this 3x kind of on its own, so that the fraction would be 1 over root 1 minus x squared. But, and there's other options too, but like this is a good start as far as a list of, some options for you. I will just mention that this first option here, u equals x, it's going to waste time. If you just pick u equals x, eventually when you go through our process, you end up with the same problem. It's just everywhere there's x's, you instead have u's. So that usually, not usually, that just ends up never being the one that you want to pick. But I included it in the list just to talk about this idea of you zoom in as much as possible. And so when you zoom in as much as possible, this u equals x is usually the first option you see. It's just not the one you ever want to pick. It turns out for this problem, the u that is best to pick, there's actually more than one option that works, but the best option here ends up being 1 minus x squared. How did I know this? That, again, I think this is only our second problem that we're going to demo. So I'd like to just kind of show you why maybe this choice of u worked by let's just go with it and see what happens. So this slide shows a lot of different options for u, but I didn't want all these different u equals options to get in the way of each other. So the next slide only mentions u equals 1 minus x squared. These other options are not shown on the next slide. So I've got the original question as well as u equals 1 minus x squared. Oh yeah, the phrasing for these is usually evaluate integral. So evaluate integral 3x over root 1 minus x squared dx was the question. And then let's go with this selection for u. You're going to just kind of have to trust me for a moment that this u is going to work. But what we should do is once you have selected your guess for u, now your guess can be wrong, but what you do is take that and then compute a derivative. So instead of calling this u prime, I'll call it du over dx again. And then to compute a derivative, this is like before, this is the first half of the semester. The 1 is a constant. it differentiates to become a 0, copy the minus sign, and then x squared differentiates using the power rule to become 2x to the first. So there's our derivative. Du over dx is negative 2x. Now we should solve for dx. That will always be the next step. Okay. So to solve for dx, the first thing to do, sorry, this text is now getting in the way, but you look from what we had right there. Look, at currently dx is in the denominator. It always ends up in the denominator because when you compute the derivative of you always say du over dx, right? So here the phrasing du over dx. The dx is always in the denominator. So as your first step in solving for dx, you're always going to want to multiply both sides by dx anyway. So multiply by dx on both sides, and you have du equals negative 2x times dx. And then to solve for dx, here we're going to divide both sides by negative 2x. Oh, I also swapped the sides, sorry. So instead of the dx written on the right side, I wrote it on the left. And then what was the left side of du, we ended up dividing by negative 2x, so that's why this now says du over negative 2x. Okay, hope we're all right with the pieces that we have so far here. This is usually the process that occurs is if you're like, I'm going to use this new method. By the way, this new method doesn't always apply. Sometimes you got to do just kind of a more plain thing like we did yesterday. This new fancy thing is not always the technique. But what you usually do kind of work like this. And so it usually requires going back and rewriting the question. Or if you have space up here to write, fine. But I think for notes right now, it's better to, like, if there was a question, we did this stuff, and then so that there's clarity when you go back and look, I think it's helpful right now to rewrite integral of 3x over root 1 minus x squared dx. Now let's make some replacements. When you get comfortable, you may choose to make more than one replacement at a time, but right now I just want to do one thing at a time so that so first of all, the dx that's right there can get replaced, and I highlighted this in red. If you need to come back and look at the slides again here, right, the dx here got replaced with du over negative 2x. Okay, that's not the only replacement you can make, but it's the only one I wanted to make right now so that I can illustrate some different points in this process. I should also say the following. I know this sounds so silly, but we'll replace the dx with du over negative 2x. Now, how are you going to make this replacement if you don't write dx? So I have people, and I get it based on what we did at least just yesterday and last Thursday, who would just like choose not to write the dx, and it didn't seem to serve any role. And so at the time I get it, but you heard me say this yesterday and even last Thursday of like, please just get in the habit of writing the dx, because look, you got to replace the dx with du over negative 2x. But how are you going to replace dx if you don't write dx? And I saw that happen. I think this is the 6th time I'm teaching 175. In the first 2 or so times I taught the class, I didn't realize where people I didn't realize why people were getting stuck. And then I realized the people who didn't write this thingy down, they weren't replacing dx, but it's because they never wrote dx in the first place. So if you don't write this, if you don't have that habit of writing the dx here, I mean, you'll want it. Like, if the original problem had a dx, please keep copying that down, even if all you're doing is an algebra manipulation. Because at some point, if you're applying this method, you've got to replace the dx. How are you going to replace dx if you don't write dx? It'll never come up. I've never seen anybody, like 100% of the time, when people don't write the dx, they never end up replacing dx. Makes sense, right? So, okay, here, the x in the numerator of 3x and this x in the denominator, in the negative 2x, they cancel. So that's the only thing I wanted to do in this step. Integral sign 3 over root 1 minus x squared times du over negative 2. And you might then say, what? But okay, so the x is canceled, but the negative 2 didn't fully cancel. It didn't cancel with the 3, not even in part, in fact. So like, then what? And I'm actually not that concerned about that somehow, right? So like, when you want cancellation, but it's the variable that you really want canceling. So we canceled x's. That's good because we're trying to get to a situation where all we have is u's. The fact that this negative 2 is still there doesn't really bother me because um, the thing is, plain numbers are going to, if they're multiplications or divisions, are going to be able to come in front of the integral in a moment anyway. So I'm not too concerned about it. There's one other, but here's the one concerning thing is there's a u, there's an x. It's not nice to have this mixing of variables. It'd be much nicer if the problem had one variable all the way through. But this 1 minus x squared that's in the root, you can replace that with a u, right? So I highlighted that in red. So you'll notice from this step to that step, the only replacement was inside the radical. Instead of the interior of the radical being 1 minus x squared, I just replaced it with a u. Again, you might work out your individual steps for a problem like this in slightly different order than me, as far as how you replace first or which thing you replace next. But I'm just doing one thing at a time. And I will, as a next step, now this doesn't have x's anymore. That's a good thing. But I'm going to just slightly reorganize it first just to have, instead of 3 in the numerator and negative 2 in the denominator, I just, in different fractions, I put it all in one fraction. And the minus sign can be the numerator or the denominator, just one place or the other, not both. So negative 3 over 2. And then this root u, it's written as a 1 over root u. Why 1 over? Because here in the previous step, root u was in the denominator. It should remain in the denominator. It shouldn't magically be promoted into the numerator or anything like this. So it's a 1 over root u. It was always a root u in the denominator, remained that way. And then the du, instead of being in this kind of awkward spot in the numerator of a fraction, you already saw some hints of this notation before. I just wrote the du off to the side. Now, you can bring this negative 3 over 2 is a number. It's a fixed number. You can bring that in front of the integral. And in addition to doing that, I did one other thing. I wrote inside the integral sign, instead of writing out 1 over root u, I wrote u to the negative 1/2 power. So the negative exponent for something that was in the denominator, and then the 1/2 exponent, because that's another way to write a radical instead. So this is rather clean, and we can now undo the power rule. So now we're ready to state an antiderivative. So I'll copy the negative 3 halves, and then to anti-differentiate u to the negative 1/2, no longer should you write the integral sign. Instead, you raise the power up by 1. So from the original power of negative 1/2 plus 1, so the new power is 1/2, and you need to divide by that number 1/2. Oh yeah, since we're done with anti-differentiation, we put a plus c there. So notice from this step to this step, we were thinking about what is the antiderivative. So there's no more integral sign. But there's a plus c. Okay, we're so close to done now. We've done the hardest parts of this. The next step is rather nice. The original question did not have u's in it. Like up here, there's no u's in the original question. We brought up u to try to make this easier to think about. So now we need to replace this u that we see right there that I'm pointing at with 1 minus x squared. So that's the one little replacement here. So everything else got copied, negative 3 over 2 times. Replace the u that appears here with 1 minus x squared, still raised to the 1/2 power, still needed to be copied down. There's 1/2 in the denominator, plus c still copied over. And we're done with the question. This is a good place to pause and see how we're doing. Are there any questions of any kind about this? There's got to be. I mean, I don't know. How did the previous class have 4 questions by the time we got to here? Somebody's got to have questions. I'll wait. Somebody's got a question, I'm sure. If you have a question, you should ask. Somebody else has that question. Okay, silent crew today. Oh, here we go. How did du over negative 2x, so this, change to that? Good question. It didn't change. This this did not change to that. These are not equal, but I appreciate the question coming up. What happened going from this step to this step is this x, let me just circle the x that's right there, and that x. There's an x in the numerator, there's an x in the denominator, they canceled. So you'll notice, like, even where the arrow is where that 3 is, there's no x right there either. Does that, I hope that addresses it. Let me maybe erase the marking. Sometimes they get in the way of seeing. So it's not that this fraction changed into that fraction, because that's not what happened. But I appreciate the question. What happened is there's a cancellation of that x and that x. Are we good with that? And actually, while I ask that question, somebody else want to bring up another question. See, I think these are the kinds of things, there's like so many little things happening. It's good to bring up this kind of thing. So I want to make sure we're all as together as possible on this process. There's still probably the big question of how the hell did you pick u? And I'll get to that question. But are there, okay, how does square root of 1 minus x squared simplified to square root of u? Yeah, so that's, you're in the, this, how do I point here? You're in that, I should actually address the question that you had, which is, so let me box that and box this, right? Okay, so the thing is, first of all, the root is the root. So even in your question, you wrote square root of and square root of. Okay, the part then that needs, so the square root signs are addressed, right? Like there used to be a square root, there still is one. The thing then is, really the question, let me, maybe I should type it to everyone back just to be clear. So then we could just rephrase the question if the square root is taken care of as, how does 1 minus x squared simplify to u? Fair to re-ask the question that way? Because the square root is there in both boxed versions. That's what's up here in red. At the beginning, we defined u to be 1 minus x squared. So if u is defined to be 1 minus x squared, every time you see a u, you could replace it with a 1 minus x squared. Every time you see a 1 minus x squared, you could replace it with a u. So maybe I'll erase my markings again. But the replacement going from this step to that step involved the stuff that's actually highlighted in red currently. So I hope that helps. And if not, let's write another question. And if somebody else has a question as well. Okay, let's then try to move on. If there's another question, bring it up. As the moment I see it, I will address it. Now, what I'm going to do is at the bottom of the slide, there's not a whole lot of room, so don't write down what I'm about to reveal. I'm going to try to save you time. There's a summary. The next slide has it written down in way more detail, but I needed to at least say the highlights of the process while we have an example worked out problem up here. So what do you do in general to make this, if this is the right process to apply, what do? You pick a u, so we did that here. How do you do it? Next slide. I'll bring this up next slide. Then what we did though was we computed a d over dx, and then we did solve for dx, which we did in this bullet point here. I mean, it took us several steps, but we got to solve for dx. Then you got to replace u and dx. So that the replacing of u, so 1 minus x squared became a u, and then replace dx. That happened much earlier on. This dx right there became this fraction. And then at some point, once everything cancels, and that's what the details that are kind of missing in this summary version, after everything cancels out, you should have this integral that only has u's, no longer has x. Like, see here, there's a mix of u's and x's in this one. That's no fun. This one has only u's, but we did a little algebra cleanup first. And so this integral that only has u's, do the integral, meaning find the antiderivative. And we did that right here. And then once you've done that, then you need to replace u again. And I call this a reverse replace. Sorry, the language is, I don't much like it either, but the thing is, originally we replaced 1 minus x squared with a u, and what I mean by reverse replace is then you replace u with a 1 minus x squared. This u got replaced with a 1 minus x squared. So this is a little too summarized, but I needed like a short version that fit here while we looked at the question that we just did. What I'd like to do then is here's the method in some detail. So what you should do is within the function you need to integrate. So look between the integral symbol and this dx. You need to pick u, right? So it's within. You got to zoom in somewhere. It's there. And how do you pick? It's partly art, but here's the hint. If you see the derivative of u elsewhere in the problem, this is usually a good choice. So having picked u, and you might be wrong with your choice, and that's okay. You just give it a try, and it's okay to like go back and change what you want for u if you need to do that. Then you compute du over dx. Once you compute du over dx, you need to solve for dx. And so the first step in that is usually multiply both sides by dx because currently dx is in the denominator. Once you solve for dx, you got to make some replacements. So you replace something so that you have u, and then you replace the dx that you just solved for. And then you want to do valid algebra cancellations. If all of the x's go away, the substitution was successful. Sometimes, especially when new at the process, your first selection, your first guess of what u is, isn't correct. And if you can't get all the x's to go away using valid algebra, you just got to go, got to go back to step one. Or sometimes the method shouldn't be this new thing. Like this is this new fancy method. Sometimes you got to use like yesterday's method. Sometimes, right? So it takes practice. But if all the x's go away, then you should have an integral that only has u's in it, no longer has x's. And what you do is you should do that integral. And that phrasing has confused people in the past, so I'm trying to include a little more language than I have in the past. What I mean is find the antiderivative. That's what I mean by do the integral. Don't forget the plus c, because if you're stating what an antiderivative is, you'll need that plus c. And having done that integral, then and only then do you replace u. You replace u back the other way, in fact. I will say that you need to do the integral or find the antiderivative, this step 6 thing, before the final replacement of u. So do step 6 and then do step 7. The usual errors I see is I see people trying to swap. I see people trying to do step 7 and then do step 6. I see people trying to combine step 6 and 7 at kind of all at once, like make a replacement and do an antiderivative all at the same time. It does not work out. Whenever people try this, something kind of goes off about the process. So do step 6, then do step 7, right? So don't try to combine the steps, and we'll see this kind of pan out in the next example. Okay, so let's take a look at the antiderivative of, or the integral of, the fraction 4x to the second over x to the third plus 6dx. Now, so far you've seen like a little short reveal at a time of many options for what u could be. I'll just list now. You don't need to write all these options down. I just want you to see, like when I look at this problem at the top, here are some thoughts of what's going through my head of like, oh, maybe some of those things might be u. It turns out, though, based on the hint, how do you pick u? You want to pick something where you'd see the derivative of what you pick elsewhere in the problem, and for that reason, you might think of picking x cubed, because if you pick this, the derivative is 3x squared, and ignoring the 3, again, the 3 will figure out what to do with. It'll kind of come out in front of the problem. Constants tend to work out, but at least the x squared part, I see that elsewhere in the problem. I see that 4x squared. I see that x squared there. So that looks promising to use u equals x cubed, and it will, in a sense, work out. But generally speaking, it'll be better to also take not just x cubed, but u equals x cubed plus 6. So generally speaking, it's not always true, but generally speaking, you want to also take a plus constant if you see that in the problem, like we see up here, this plus 6. Why? It's because once you pick u, you end up differentiating u, and the derivative of a constant is 0 anyway. So let me, on the next slide, hide all these options for u because they'll get in the way. So I've got just the original problem and this choice for u. So going through these steps, we should differentiate. Du over dx is 3x to the second plus 0. The derivative of 6 is 0. We need to solve for dx. meaning our first step should be to multiply by dx on both sides because it's in the denominator. So multiply both sides by dx. And to solve for dx, we divide both sides by 3x squared. So du over 3x squared is equal to dx. And now, there's the original question. Let's make some replacements. This time around, I'm going to be a little fancier and make two replacements at once. So do you see them? I wrote the integral symbol. I wrote the 4x squared in the numerator, but where the denominator was an x cubed plus 6, I made this replacement that x cubed plus 6 can get replaced with a u. I also replaced the dx with the fraction du over 3x to the second. Now, check out that the x squared on top and the x squared on bottom cancel, standard algebra cancellation. So you're left with 4 over 3. So 4 in the numerator, 3 in the denominator. Sometimes what happens in these problems is people move things from the denominator to the numerator without like changing the exponent to be negative or whatever that needs to happen. So be careful with that kind of thing. But 4 over 3 over here, so 4 over 3 there. The u was in the denominator before. The u remains in the denominator here. So it's a 1 over u. And then the du is in a numerator of a fraction, but I just wrote it off to the side. I prefer this off to the side. The 4/3, you can write it in front, but the key point is, you copy down the 4/3, and then you need to anti-differentiate. So there's only u's. And when you anti-differentiate one over u, you get ln of absolute value of u plus c. So this is us computing the antiderivative going from here to here. That's why there's this plus c and no more integral sign. And then finally replace the u with x to the third plus 6. So 4/3 ln of absolute value of x to the third plus 6, close absolute value, plus c. And just to point out what I was trying to talk about in the warning on the previous slide is that first you compute the integral. That step 6 thingy was, here's the integral. The integral is computed. Find that antiderivative, in other words. And then once that's happened afterwards, after that, then the u gets replaced with x to the third plus 6. People try to swap the order, but if you swap the order, if you take this problem and you start replacing the u, then you actually, before doing an antiderivative, you have x's and u's mixed in the problem again. That's not a good idea. So I know that was a little much, but I just, stepping back here, I hope all the pieces start to fall into place a little bit, and you're seeing a little of the insight behind how the art of selecting u is done. I knew we would not probably have time for this next problem, but I have it here for you to look at some point later if you'd like. Tomorrow we will start class with a problem that's similar but not the same. So it's just, you could look through question 265 later if you'd like. But I just, since it's a Tuesday, I wanted to make sure to end class by saying, please be sure to do the online quiz that is dated for today. And then I would strongly suggest starting WebWork 36 today. Sometimes people are in the habit of starting the assignment that is due this day. That would be assignment number 33. But please consider starting assignment 36 today. And see you in office hours or see you tomorrow.